Hey, it looks like I'm live. All right. Well, hopefully this is the talk you intended to be in, how to use Constexpr in C++ plus 23. You know, I left this slide intentionally poorly done. Of course, I wrote C++ 23, but this is just my chance to rant that if you do anything with like line breaks and typesetting and layouts and stuff, C++ is a thing, right? It's not, there shouldn't be a break between those two pluses. That's, all right, my random rant. Okay, so my name's Jason Turner. I accidentally clicked on the wrong thing there. Oh. Yes. That is the point. That's the QR code, but it's a new feature of my slides. QR code, you can take a picture. It'll take you to the thing. Apparently, if I click on it anywhere near it, it'll also take me to the thing. So C++ Weekly, I've been doing this since 2016, and that's a link if you haven't heard of the YouTube channel. And I have stickers for anyone who might want stickers. So don't let me go home with those. I also I've written a few books, and I do training, and I am a developer. So if you like the way I do things, consider having me on site for training at your company. And there's a few people here who have had me on site for training at their company, so I appreciate that. I like to say avoid sitting in the back or sit towards the front, but with this room that's irrelevant. But I do want you to interrupt me and ask questions. And I'll be asking you questions. So hopefully we'll be able to interact with each other. Okay. Who went to Hannah's talk yesterday? I'm glad you were there. Okay. Hannah talked a lot about Constexpr and what is possible in Constexpr with what versions. In general, it is easier today to say what is not allowed with Constexpr than to say what is allowed. Is that fair? Okay. And the things that we're going to talk about, the rules about what are and are not allowed in Constexpr, come down to when things are actually being constant evaluated. So I don't just mean what's not allowed in a Constexpr function necessarily. So the first rule that I wanted to highlight, which I thought this was interesting because I was just rereading the rules, is that you cannot deallocate memory that was not allocated during constant evaluation. The more I think about that, I wonder how in the world you were supposed to ever get a pointer to memory that was not allocated during constant evaluation, but that's one of the things that was listed. We cannot use reinterpret cast. You cannot use or be a coroutine yet. You cannot execute an assembly block. So to be clear, you can have one in your const eval or Constexpr function. You're just not allowed to actually use it. You cannot execute a goes to statement. It can be in your function. You're just not allowed to actually execute it during constant evaluation. I find that rule particularly interesting because we're allowed to have switch statements with cases and labels and such, and those are allowed to be executed during constant evaluation. Why are go to statements not allowed? No, you can't jump out of scope. Can you? I don't think you can. You can't jump out of function scope, right. And if you do jump out of scope, then destructors still have to be called correctly. I did an episode on this. Someone should watch it and remind me what it said. You cannot have virtual inheritance. You cannot throw. Yet, says Hannah. You cannot invoke a non-Constexpr function during constant evaluation. You cannot invoke undefined behavior, asterisks, I guess, because that's kind of up to implementation quality a little bit too. You cannot invoke a VA start macro. I thought it was interesting. I thought Constexpr functions just couldn't be C variadic functions, but apparently maybe they can be. You're just not allowed to actually use any of the arguments to it. I don't know. Plus, any memory allocated at compile time During constant evaluation, it must be freed at compile time during constant evaluation. For now. Okay, so I have a Constexpr function that unconditionally throws 42. On line 8, am I executing this code at constant evaluation at compile time? I am not. This code is fine. This code compiles. It's not a very smart use of Constexpr, but it does compile today. This, however, does not compile because I am, in fact, forcing evaluation of this function at compile time by assigning the result to a Constexpr variable. So some of these things only matter, like I said, during constant evaluation. So this is a pro tip. Make sure you test your Constexpr functions both in Constexpr context and in non-Constexpr context. Actually, just had a conversation with someone yesterday afternoon about that. Who was it? Are you here? Not here. Well, anyhow. So I don't have any slides on this or anything, but if you do have a bunch of Constexpr code, you should, I say, ideally, compile twice. You want to compile once with all of those tests being executed at compile time, some sort of macro that makes the variables Constexpr, and some that make the variables not Constexpr. So for two reasons. One is to make sure your code does the same thing, whether it's being executed at compile time or not at compile time. And for the other reason to be, if your code fails to compile, because you did something you weren't supposed to do during constant evaluation, that is extraordinarily hard to debug. Yes?
Which test framework are you using?
Which I use catch2, and I use the static require macro, and then I compile once, normal, and the second time I compile, I pass the -d runtime static require. I think that's what it's called. Where's Martin?
It is static require.
Oh, it's just, oh, okay. Yeah. But whatever it is, runtime static require, yeah, to put it, force it back into runtime mode. And then I compile my full test suite twice and then run them both on CI. And the ones that were compiled with normal static require, running them at runtime, running the tests that were compile time checked at runtime, just gives you a bunch of print statements, basically. It doesn't actually do any work, right? And then when you run the regular runtime ones at runtime, then you can actually step into the debugger or whatever if you need to. All right, a little bit of context for how I got here today. C++ 11, simple Constexpr usage, not very useful. C++ 14, we actually got control flow, variables, and some usable Constexpr. I would say it starts to become usable. 2016, I gave a talk called Practical Performance Practices at C++ Now. And in that talk, it's actually kind of funny, because I'm like, yeah, I don't trust Constexpr. Made my code worse somehow. I didn't trust the compiler on this stuff then. 2016, I gave a talk, Rich Code for Tiny Computers, which everyone thinks was about Constexpr, but I don't actually use Constexpr in that talk at all. I use const, just plain old const. 2017, Constexpr lambdas, much better array support. Like trivia time. When did standard array actually get full Constexpr support? 20? And what was the last thing lagging? Do you recall? No? What? No, not begin. No, begin end we got fully in 17, read and write versions. No, not that. It was fill. And my understanding is because fill, it was defined in terms of standard fill, the algorithm, and standard fill, the algorithm, didn't become Constexpr until C++ 20. Well, random things. 2017, Constexpr all the things, talk that I gave with Ben Dean. That was definitely about Constexpr. In 2017, practical Constexpr, again, that was at Meeting C++. In 2018, I gave this talk, Applied Best Practices. I tried to write a new greenfield project from scratch, applying all the things that I say are best practices, and I accidentally made a fully Constexpr-capable ARM emulator. You can execute a bunch of ARM instructions at compile time if you choose to. And C++20, most of the algorithms, better standard library, vector, string, new, const-eval was added. Const-eval is going to come up in a minute in this talk. In 2021, your new mental model for Constexpr, another one of my talks. And then the power of compile time resources in 2022. In C++23, we get Constexpr CMath, except for the trigonometric functions, and even more relaxation of the rules. In 26, have we gotten fully accepted the trigonometric functions for Constexpr? I think so. In 23, I was again playing around with this stuff, and I made an embedded scripting engine called Constexpr, which is a fully compile time capable scripting engine that's non-allocating, non-throwing. You can configure its size at compile time for like its actual memory size and whatever. You can execute script at runtime or compile time. And then a talk I just gave at CBPCon, and not CBPCon, CBPCon's in next week. Sorry, I've been traveling too much. I gave it C++ on C, called Understanding the Constexpr two-step. That talk is live on YouTube. I do recommend it. I think it came out pretty well, so if you want to watch that one. And then here we are. OK, how to use Constexpr in C++23. All right, C++26, Constexpr placement new has been accepted. I think we have the rest of the trigonometric functions from CMath and C++26 as well. And if you were in Hannah's talk, she has plans. OK, so why Constexpr? Work done at compile time doesn't happen at runtime. Is that a compelling enough reason by itself? If you can do work at compile time, would you rather do work at compile time? Who says, no, I prefer doing as much possible work as at runtime? No one? Oh. OK, so compile time work is paid once at compile time, not at runtime. I do have people who push back and say, oh, but that Constexpr stuff is going to slow down my builds too much. It tends to be people who haven't actually tried to use Constexpr that much who have this complaint. And then there's those of us who actually have done projects where you have to do like pass command line parameters to your compiler to increase the number of Constexpr steps it's allowed to execute. But that's a different problem. Is your code executed more times than it is compiled? You really hope, right? If your code's executed exactly once, then none of this matters. By definition, Constexpr code that is executed at compile time cannot have security vulnerabilities. The code simply doesn't persist. All right, Hannah, go ahead and make your argument. No? Oh, fine. You're the... yeah. Who wants to make an argument that code that is executed at compile time can have security vulnerabilities? You want to. Later? This is important. Martin, yeah, go ahead. OK. OK, so if the compile time code generates something that would be like a bad hash, then you're going to have that bad hash into your runtime code. That's a fair statement. Constexpr or code executed compile time, quote, cannot have undefined behavior. As I already said, that's implementation quality. It's not 100% enforced by all compilers, but it's pretty good. OK, let's build a unique pointer. Do you see my unique pointer implementation and the set of tests that I have? Go ahead and stare at this for a moment. See if you find any bugs in it. See if you think it has a full test suite. Okay, so Bryce says we're leaking memory. Yes, I'm expecting you to find bugs. Anything else?
Move operations don't do what you'd expect.
The move operations don't do what I expect. Okay. I mean, but I'm following all my best practices, right? I didn't implement any of the other special member functions, so I'm good. Rule of 0. Oh, by default, pointer is uninitialized. Yeah? All right. Anything else? Yeah, that's a good question, whether that's a bug or just poor implementation. The comment was the single parameter constructor is not explicit. You probably want it explicit here. Yeah. No make unique. Let's call that a not part of this problem at the moment. It's incomplete, but not broken. Yeah.
The dereferencing operator doesn't check if the pointer is initialized.
Ooh, that's interesting. The dereferencing operator does not check if the pointer is initialized. If we want to pick on the standard library and say that I'm trying to implement a stood, if you will, unique pointer, does its dereference operator check? It does not. That might not be the best choice, but it does not check. But then people would complain that, hey, unique pointer is slower because it has these branches every time I go to access it. So, that's a thing. Okay, but if I were to actually compile and execute my test suite, I would get pretty good code coverage and no bugs, right? All right. How would I go about making unique pointer Constexpr? Just kind of see what I'm doing right there? Sprinkling some Constexpr around my code, like that. Okay, so how do I now test my Constexpr-enabled version of unique pointer? You can follow along if you would like. QR code, this will take you to Compile Explorer.
Given us a QR code, which we have to scan with our phones, Compile Explorer famously not great on mobile.
That is fair, and I'm not going to repeat it for the video. No, it's true, yes. Compile Explorer is famously not great on mobile, but it is better. It does reflow the layout. You can look at the code. You can follow along a little bit. Things that were separate windows are tabs, should be if you scan that. But I thought some people might want to. It's an experiment. Give me a break. All right. So this is what that's going to take you to. I have unique pointer with some Constexpr sprinkled upon it, and then I have a bunch of const-eval tests. So by simply wrapping these operations, I admit this is going to look weird, but it's also awesome at the same time. I have immediately invoked const-eval lambdas. That's what every one of these lambdas is. If you're not familiar with the syntax, open bracket, although I think you all are, lambda introducer, and then I'm explicitly making it a const-eval lambda, and then I have my test case in there. It's smooshed up a little bit more than I would prefer for the sake of getting it to fit on one slide. And then at the end of each one of these statements, like a line 15, empty braces, semicolon, empty parens, semicolon, to immediately invoke that lambda. So I'm forcing this test case to be executed at compile time. Has anyone done immediately invoked const-eval lambdas to force work at compile time? Oh, come on, you have to try this. It's really fun. Okay. This is what we have. So you will note that my const-eval immediately invoked test case fails to compile. It says call to const-eval function, looking at the top one here, blah, 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 is not a constant expression, and constant expansion of whatever, accessing uninitialized member PTR. One of you called that out. You're right. The default constructor of my unique pointer, in fact, does not default initialize PTR. And the compiler caught that for me because I tested this at compile time. So let's go ahead and initialize that with null pointer. And now we can see, because the squiggles went away, that the first test case now passes. My second test case is very simple. I'm just initializing a unique pointer with a pointer, with a new int. And this test case is not passing at compile time. It's failing to compile. Why is it failing to compile? Because I'm not deallocating. And if we were to try, the problem is some of this can be difficult to read. It's not a constant evaluation, blah, blah, blah. Because allocated storage has not been deallocated. Well, thank you very much for compiler for letting me know that. So I now need to provide a destructor. Does that seem like a reasonable destructor here? It's either going to be null pointer or it's going to have a value. I don't have any way to check to see if it's actually a valid pointer. It should be all right. Maybe. Deallocation of already deallocated storage. What is that about? Okay, so this test passed. These two tests passed. And now my next test case, where I'm attempting to move my unique pointer to another unique pointer, that test case now fails at compile time. What do I need? The move constructor. Here's a fun trick, by the way, if you're not familiar with this one. It's one of my favorite use cases for this tool. I am going to initialize pointer with the result of the exchange of others pointer and null pointer. So what I'm doing is assigning others pointer to null pointer, and I'm assigning my pointer to others pointer. All right. Now I have another test case. That is failing. Use of deleted function, operator equals. So it's telling me that the copy assignment operator has been deleted, which, yes, thank you, compiler, for deleting the copy assignment operator. That's actually the right thing to do here. So I'm going to go ahead and provide my own. Move assignment operator. That looks mostly right? Is there? Oh, okay. Now, this is the part of the story where we show that you still have to have reasonable test cases, right? This is not a perfect implementation of my move assignment operator. It is missing something. It's using what? I need to return something. Oh, right. So I actually do have a compile error there. Look at this. No return statement in Constexpr function. That's a hard compile error. Otherwise, it's a warning, and you hope that you have warnings as errors. But in Constexpr evaluation, it must be. So that's not even the thing I was going for, though. The problem is if, well, let's go ahead and finish this, and then we can look at the other things. Oh, no, wait. Actually, there we go. Sorry. Yeah. It's not a constant expression because allocated storage has not been deallocated. So now my very last test case fails because, yes, I have to make sure I clean up my own storage. And now my code compiles. So by enabling this for Constexpr usage and making Constexpr test of the things, I know that if this code compiles, it is correct and it doesn't have undefined behavior. my destructor can throw? That's an interesting point. So do I just mark this no accept? So my destructor's no.
Delete can throw. The delete or the pointer can throw.
Yes.
And you're not testing it.
Right. So delete of the contained thing might throw. So how do I implement my conditional no accept? That's if I'm getting where you're going with this. I believe that's right. No accept of the delete of the pointer. It's correct, though.
It's correct, but don't do this.
OK.
It's not unique. It's not super unique pointer now.
Is unique pointer unconditionally marked to no accept, or is it conditionally no accept?
STD classes don't do no accept this.
OK. STD classes don't do the no accept thing. This is, yeah, it's ugly. But what it says is my destructor is no accept if deleting the contained thing is itself no accept. It's ugly. It's not the best way to do this, but it technically met the requirements. OK. There are other things in here that I'm not fully testing, of course. So you do still have to have good tests. And there's a little bit of a problem of trying to figure out what your test code coverage looks like if you're doing this 100% at compile time. So it's another reason to compile your compile time test at runtime, basically. All right. Well, is there any other questions or anything anyone had here? All right, I saw a picture being taken, so I stood back. All right, what version of C++ was required for that? 20, yes, 20. 20 was required. So I'm going to play a little game. This is all of from the C++, it's an implementation of stood all of from the C++ standard library. What would it take to make this Constexpr? I'm going to get you all acting this out in a minute. What do I need to do to make this algorithm Constexpr? What do I need to change? It's like this, right? Just a little bit of sprinkling. Just add Constexpr to the front of that. It's Constexpr. What version of C++ would be required to sprinkle Constexpr on all of? 14. 10 years ago, if I have my year correct. I regularly have to ask what year it is. So we sprinkle Constexpr. All right. There's this book that I recently, I bought it 5 years ago. I recently opened it and looked at it, called Scientific and Engineering C++ by Barton and Nachman from 1994. This is a classic in some worlds. You have this book, and I guess that's probably because I know something about your history with national labs and such is why you have this book. Does anyone else know this book? Oh. So I'm flipping through the examples just for the record. They're shockingly well written for pre-standard C++. So I found this example in Scientific Engineering C++. Take a minute, look at this, see if it reminds you of something. Does this seem familiar to anyone? Expected. Yeah, it looks an awful lot like standard expected. It's something that either is an error or holds a value, a valid object. It's intended for returning from functions. Like, these people were 30 years ahead of their time, pretty much here. Okay, so what would it take to make this piece of 1994 pre-standard code Constexpr? You don't have to have union. Hannah said union, which would imply C++ 14, we're allowed to use 17, we're allowed to use 17. No, in 17, you're allowed to use unions. You're just not allowed to change the active member of a union until C++ 20. Right, the code on the screen doesn't use the union. So this code would, as it stands for full complete Constexpr usage, would require that the contained type be Constexpr default constructible. Otherwise, you couldn't really use it in Constexpr usage. Oh, no, that's not true. Just as long as you never called the default constructor of this one at compile time, it would still be good. All right, so we sprinkle Constexpr, and it would work in 14, right? Okay. Here's another example from Scientific Engineering C++. This is their interval type. It's kind of like a range, but it's just numeric range, or span kind of thing. So they've got, the interval class with high and low, and constructors and const and non-const. But this was separated between header file and C++ file in their example. What would it take to make this Constexpr? What's that?
Move it to the header.
Oh, Bryce made a really good point. Just for the record, yeah, this as it stands could be C++ 11 Constexpr. I had not thought about that. Now, the problem, just since I didn't put anything on a slide here, in C++ 11, a Constexpr member function is itself implicitly const. That was removed in C++ 14, but this doesn't have any mutating member functions. So yeah, we could have made this Constexpr in C++ 11, but someone else pointed out, move the C++ implementation up into the header. Is that technically required? Yeah,
Well, there's a different question between having it in the header versus can it be out of line.
Yes, exactly. Having it in the header versus can it be out of line. I believe it can be out of line in C++ 11. A definition must be available when you go to execute it at compile time. Technically, you could move this into a .impl file or something, but practically speaking, what are we doing with this code? Lifting it into the header and then sprinkling. And we're all going to be acting by the end of this. So I've got 20 more minutes to get you acting, okay? 27 more minutes. Okay, so like that. And this would be valid in C++ 11, but I think you might get an actual warning with older compilers because you marked a Constexpr function const and it was already implicitly const. Yeah. Practically speaking, C++ 14. All right. This is also from Scientific Engineering C++ and Engineering C++. This is their array shape struct. Virtual member functions, virtual destructor, and then some inheritance going on. Why not? I cannot make this Constexpr because I have virtual inheritance. I have a virtual base class. My pointer is not doing what I want it to do. Oh, do your job. Okay. A lot of people do confuse these two topics, so I'll take just a second on here. These are virtual functions, right? This is virtual inheritance. It is a base class specified with the virtual keyword. Why does that feature exist? The diamond problem. Yes. So if I've got some base class, another derived, and then down here that inherits from both of these two things, if I don't have virtual, then I actually have two instances of that shared base class. If I have virtual, then those two instances get merged into a single instance. C++ still does not allow virtual inheritance. Is that one of the papers that you had mentioned or not? Okay, so there's no even any plans to allow virtual inheritance. So if I wanted to make this Constexpr capable, what would I need to do? I legitimately have to re-architect this thing, right? Because it's relying on this diamond inheritance thing. Although I didn't actually play with it, given that the thing that is being inherited by virtual inheritance is itself it's pure virtual. It's an abstract base class. I was like, do I really need virtual inheritance? Is it okay to have two separate instances of that array shape? I don't know, it sounds unwise anyhow. Okay. So I asked Twitter for code that I could use in this talk, but I didn't actually tell them why. I thought about I should have a slide that says Twitter, formerly known as Twitter. If you're still on Twitter, you know what I'm talking about. Again, codes, you can scan them. These take you to GitHub. You can look through the code with me if you would like to, or you can just stare at the screen. This is a library for generic nonlinear undo redo functionality. So you can register events and then have an undo history and undo things. So I started clicking through this. I've got undo state.h. Let's see. What would it take to make this header file Constexpr? Did anyone see anything sus in it? That's the whole header file. Seems fine. I can probably just sprinkle some Constexpr. There's a couple people playing along. Thank you. Too bad I didn't bring any extra swag. Give it out. Okay. Undo history.h. Let's see. Namespace undo, virtual destructor, virtual void, constructor. Yeah. Okay, so those are declared out of line, or defined out of line. The add, can undo, can redo, undo, redo functions. Clear, redo, these things are out of line. Delete first, okay, move to. All right, does it look like I can, for the most part, so far, I can just sprinkle some more Constexpr in here? Sprinkle, yeah! We're gonna get everyone doing this, yes! All right, undo command. Lots of virtual in these things, but whatever. Well, let's definitely sprinkle some Constexpr, although I would do one minor code review on this. Does anyone see it, since I do best practices and I have your attention right now? Equals default is great. Don't put those empty braces on our destructors. I mean, it's practically speaking, since it's virtual, it's not going to make a difference, but just let the compiler do its job. Equals default. Yeah. All right. So then that leaves undo history.cpp. Oh, you're actually following along, are you? Yeah. So most of this looks pretty good. There's some asserts. We're going to have some trace logging.
But it's the default is just to define it from empty macro.
Yes, I did see that. Yeah, I didn't see that when I've looked through it before, but it does have just an empty macro right there. So I guess it doesn't matter? Right. So the comment that Bryce just made was the error handling generally doesn't matter during constant evaluation, because if it were to hit that path, the assert were to fail or whatever, then you're going to get a compile time error anyhow. But if you have logging macros like this in here that actually do something, you might need to do something like wrap your logger in a if not const eval, or if not is constant evaluated, depending on your version of C++. You might have to deal with that in some place. Raw, new, whatever. Where was that? It was down here somewhere. I know you already saw it, Bryce, because you mentioned it. Ooh, uh-oh. Uh-oh. Standard stack. Is that Constexpr capable? Not yet. Sorry, I just pointed at the person I know. We'll get there. And then there's this. Can I const cast at compile time? I think yes. I'm pretty sure yes. It's not in the list of things that are explicitly verboten, like reinterpret cast. And I meant to actually test this, but can I modify a const object? No. So definitely 100%. If this code actually invokes undefined behavior by mutating an object that was originally created as const, now I've just opened up an entire new pathway for the compiler to find undefined behavior for me. I just have to execute the test and find out if I am invoking undefined behavior by modifying a const object. Spectacular. All right. Yeah, and then delete. OK, so we have, let's see. Most of the code's already in headers. Some questionable const cast. We think that should be Constexpr capable. Would you ever use an undo framework at compile time? Probably not. Probably not. But it enables this new range of tests and possibilities. You don't know how the users of your library might want to use it. This is from the same developer. They were eager to send me examples on Twitter. So this is a minimalist string tokenizer. Interestingly, their comment to me on Twitter was that you probably don't need string tokenizing at compile time. Said that just for Hannah's sake. Yeah, so string tokenizer, let's see. This is 100% header code. Just let me know if you see anything that concerns you. It's a pretty small header. Is anything? I don't even see a standard library call at all, except for into standard string. So what do we think? How do I make this Constexpr? Sprinkle some Constexpr on it. It's all it's going to take. 100% headers. Let's sprinkle some Constexpr around. This is from Joel. Task sync. This is an interesting one. Task sync. Let's go ahead and just drop into one of these header files. Atomic, string, cassert, thread, mutex. Which of these things can be used at compile time right now? None of them, right? Like, we can't do multi-threaded programming at compile time. We can't attempt to right now. We can't. Standard thread is not Constexpr. Mutex is not Constexpr. Atomic is not Constexpr. Yet. Shared pointer is not Constexpr as well. Yet. But I don't know. So OK, so this is 100% headers and module interface files. Stuff from thread and mutex and whatever. Do Constexpr threads make sense? Yes, says Hannah. Who says yes? I want to be able to do Constexpr threads. All right, all right. So interestingly, and this, just for the record, it's coming straight from Hannah here because of chats that we had before. If we have Constexpr threads, there's some possibility, because deadlocks and races are UB, and we're not allowed to execute UB at compile time, that we could, for some definition of prove our multi-threaded code correct at compile time if we were allowed to do these things at compile time. It's kind of like for some definition of probably maybe, but that's not the point. The possibility's there. All right. Oops. Well, whatever. UChemL tools. Oh, I didn't leave the link up long enough. This is linked to the wrong place. That's not helpful, is it? Oh no, here we go. Actually, I should probably start moving a little faster. Yeah. Okay, well, no, let's just stop here. This is great. All right, I jumped into the first piece of source code that I found. Can I sprinkle Constexpr on this code? No. Why? Because of map. At least not yet, right? If we got Constexpr map, then this header file at the very least would be good. All right. This actually does have a lot of code in C++ files, but let's not dig into that. Ultimately, after my going through it, we would need Constexpr unordered set, Constexpr map, and Constexpr ostream. Do you want Constexpr ostream? Oh, well, that was easy sell. Everyone said yes. You need virtual base classes for this to be implemented. It's one of the few places in the standard library that actually does this diamond thing. And just for the record, for those of you who might be a little confused about this, ostream is not just used for file I/O, right? It's also the base for string stream, which might then give us compile time string formatting. Yeah, I'm okay with this. I don't remember this one. This one relies on C SAT solvers, so that's a problem. You can't really so much call C libraries at compile time. Is that am I going to get a yet on that one? Robert?
We have Constexpr objects only.
Yes, Constexpr objects only. The probability of C getting Constexpr for function declarations in our lifetimes?
We got the keyword now.
Okay. Yeah, the hardest part is that the keyword exists in C now, so it's possible. The high-level interface itself can be Constexpr. And just as an aside, this thing does rely on throw and catch. Does it make sense to be able to throw and catch exceptions at compile time? One answer says yes. I think the real takeaway here is, like, besides the fact that it opens up a whole new way of testing our code when we have Constexpr enabled for our libraries, and ways for users of our library to use our libraries in ways that we never imagined, it's like, well, in Hannah's talk when she was talking about Constexpr coroutines, if a coroutine is the best way to represent that problem, then I want to be able to represent that problem with coroutines at compile time or at runtime. Like, why limit that capability? If the best way to solve your problem means using throw and catch for exception handling, then why not be able to do that at compile time as well? Well, I had a lot of these, didn't I? All right, this one is interesting. I'm going to go ahead and dig into it. Find devices. Let's actually look back at it. Audio device and serial port search utility. Does that immediately scream like, I definitely want to look for audio devices and serial ports at compile time? I'm getting some nods. Yes, actually. Are you hoping at compile time to have your compiler be like, warning, or something? That would be pretty cool. This is the kind of thing that's got a lot of hardware-specific operating system kinds of things. Should it be Constexpr just as a general? No. Yeah. What? Bryce says yes. All right, you're on the record now.
Maybe
No.
you want to do your tests and you have like a emulated or fake audio device.
Right.
That you want to run your tests with.
So you could have an emulated or fake or dummy device or what's the word I'm looking for? Yeah, a mock, thank you. Mock device or something like that, that you could actually test the rest of the interface at compile time and see if the rest of the interface is good. So this is where I ask, maybe if this is the kind of project you're working on, you should ask what portion of this project actually can be Constexpr. To think that your entire project can be Constexpr is probably unrealistic for most problem domains, but considerable portions of things can be. 9 minutes and 55 seconds. Let's see what the next one is. Different implementations for finding robust random member minimizers in genomic data. Does anyone know what that means? No? Genomes are cool. Why not? So vectors, lots of vectors, vectors. That's easy. Already he's got some inline Constexpr arrays of things. Win-win. GNU always inline. Accept. Most of this looks pretty straightforward, just looking at the header files, right? Like, I should be able to just sprinkle the Constexpr around. What's that? They're already sprinkling Constexpr, but not on all the member. Oh. Uh-oh. No. What's the prognosis for reinterpret cast at compile time? Never happen? Oh, well, never mind then. There probably is some integer overflow shifting stuff. But yes, that's also a good point. If you invoke undefined behavior for like integer overflow, shifting too far, that kind of thing, that's also a failure to compile. So this would be possibly opening up a whole other way of testing this code. Oh, there we go. Yes? Is Bitcast, yes, Bitcast is Constexpr. Bitcast doesn't let you reinterpret cast a pointer. You would need to do the whole like bitcast it into a new object and then work on that thing, which is great. That's a good use. I mean, you know. Then there's also begin lifetime as, which is a C++ 23 feature.
Isn't Bitcast not Constexpr for pointers?
Yes, that's my point. It's not Constexpr for pointers, so there would be like we can't do that. Yeah. But you could bitcast the underlying objects. Yeah. And then start lifetime as C++ 23 that 0 compilers have implemented so far. That is not Constexpr, but I think Hannah's going to work on a proposal to make that Constexpr as well. All right, so we would need deck to be Constexpr. Is deck Constexpr? Not yet. At least half of that code's already in headers. So the standard library. What parts of the standard library are not currently Constexpr? If you were in Hannah's talk, you've already got a pretty good handle on this. Everything. It's a lot of standard library and stuff. I am going to go ahead and congratulate Hannah here on this work. This is her commit for the LLVM project, the standard library. This is making how much of the standard library Constexpr? Only containers, but a lot of containers. Deck, list, forward list, map, unordered map, unordered set, flat map, flat set. Oh, but the other adapters are stack. Okay. Notice if I scroll through Hannah's commit for making the standard library Constexpr, what do you see? It's like this, right? Let's go ahead and zoom out a little bit. For like thousands of lines of code, just add Constexpr. And wait, before that, Hannah, I have another link to that paper as well. Hannah's implementation experience with this is in her effort to make all these Constexpr, she actually found undefined behavior and bugs across the standard library and fixed them in the process. Yes?
Can you go back to the top for a second?
Go back to the top for a second. Yes?
When did memcopy become Constexpr?
When did memcopy become Constexpr? Hannah says a long time ago. The initial set of algorithms, says Bryce. That's actually, I was like, I didn't have an answer for that one. Although, good eye to have caught that. Yeah, so, I mean, look, Constexpr sprinkled everywhere. All right, this is Hannah's implementation experience. Yes, thank you, Hannah. This is Hannah's implementation experience. If you want that link, and it's that paper with all those changes, plus the bugs that she found in the process. Oh, sorry. Yes, there you go. And, oh, no. Ah. Well, that doesn't help there. Change the URL from D to B? To P. Oh, no. The link was taken down. All right. You can see her actual paper is literally thousands of lines of adding Constexpr. All right, so change the D to a P. Should have checked that link before I came here. That's all right. So, how to use Constexpr in C++ 23. Avoid the standard library functions that are not yet Constexpr. Step 1. Avoid throwing and catching exceptions at compile time. This is 23, keep in mind, we might get these things in 26. If it's already in a header or interface, it should already be Constexpr. If it's already in your header or in your interface file, there's a very good chance you can sprinkle Constexpr on it. You might have to move code from into module interface files or into header files. And if you move them into module interface files, let's just say it's fine. They're just like really good pre-compiled headers. So you don't have to worry about reprocessing this, reparsing this stuff every time. Is Danielle in here? No. OK. And then mark them Constexpr. Sprinkle some Constexpr. You might have to do things like put loggers in const-eval blocks or put those inside your logging macros. What? If not Constexpr, yes. And if not const-eval, or if not is constant evaluated. But if we're in 23, then if not const-eval. Which looks really weird if you've never seen that, by the way. It's literally if, exclamation point, const-eval, open brace. So it's an if statement that doesn't have a conditional because the conditional is implied in the if statement. It looks strange. Like that. Test both at compile time and at runtime, and then profit from better flexibility and better testing with your code, because you don't know how people are going to use it. I am going to wrap up here, but Ashley Roll, I'm not going to click on it. Ashley made a compile time music sequencer. So it's got a DSL. Oh, you know what the heck, I'll try to click on it, because I do have a minute. Oh, that's the implementation, not the example. It's fun. It's not a practical thing, but the point is that it wouldn't be possible to do these fun or necessary things without having, there we go. It's a DSL that Ashley made that parses that music sequencer for the notes and everything at compile time, and then it generates a WAV file. It's fun. But it relies on using things like vector and string internally, things that you wouldn't have necessarily thought needed to be available for Constexpr use. All right, I am out of time. But this is who I am again, and if you have any interest in having me for training or anything, please contact me. And you can come up and ask questions afterward, and I have stickers. Otherwise, thank you very much.